Sandra, Wolfgang, everybody is here. All right, I haven't had my coffee. I had a cup of tea, and that's not really working. So if I fall asleep in the middle of the class, you know what's going on. So we started talking about alkenes. We talked about alkene. We talked about alkene double bond. The fact that when you have a double bond, one of the two double bonds, again, don't think, try not to think like too much of like a physical picture. Like one bond, it's not as simple as you know, like two bonds, like a one rope that's made out of a steel and another rope that's made out of cotton. Okay, it's not like that. All the scientists know, you know, in case somebody is wondering in this classroom, in case of you guys are wondering, like, what, is there really a sigma bond? Is there really a pi bond? Is the only pi bond that's sketchy? That's the sketchy part of that bond. I don't think so. I think these are hypotheses and these are theories that chemists and other scientists sometimes come up with to explain the results and the phenomena. Okay, so what do we know about single bonded species and double bonded species? We know that the single bond is longer. Okay, if the single bond is about from my elbow to my wrist, okay, the double bond is shorter, and a triple bond is even shorter. We know that. Okay, we know that. We also know that the double bond reacts with stuff that single bond does not. So we know that part of the double bond is little funny. Okay, part of the double bond is more reactive, and the double bond wants to be a single bond. A triple bond wants to be a double bond, and a double bond wants to be a single bond. We will see some of the reactions today. Okay, so we're going to lecture until 9:10-ish or 9:05-ish. I need to double check the exam, just make sure that all the questions make sense. There are, don't freak out, there are 32 questions and you have to do like 28. Okay, each question is 2 points, so 28 times 2 is 56. So the total points for this exam, the midterm, is 56 points. Good morning. Who is this? Somebody is joining. Don't know who it is. Okay, so if you get 28 right, then you get 56 points in this exam, in this midterm, 100%. If you get the 29th right, then on top of 56, you get another 1 point added. So each additional correct question will add 1 bonus point. So you can get up to 60 points. If you get all 32 questions correct, then you get 28 times 2 plus 4, 60 out of 56, which is close to 10%, like 108% or something. Make sense? Maybe I'll pause, practice pausing, practice my times of silence, moments of silence. Think about that. If you have any questions, it's not something that I want to discuss, but if you really have a burning question, you can ask me right now. Then we'll go back to alkenes. Makes sense, right? Okay. So we talked about very quick review of, you know what we should do? Let's do a little mini review at the very beginning. What I'm going to do is, this is something that I didn't think about it, and like sometime toward the very end of my Chem8 class in spring, right? We're in summer, yeah. In spring, I just realized that, if I were a student in my class, in Shantanu's class, this is how I would sometimes flip through the pages. You know, like sometimes you flip through the pages of a textbook and kind of see, like, glance at it, and that gives you an idea that, yeah, electronic configuration, okay, I got it. Different orbitals, I got it. Tetrahedrals, sp3, got it. then double bond, then electronegativity, bond structure, polarity, alkanes. They can get branches. This is what the branches are called. So what I realized that if I go to canvas, my canvas, like the way you guys see our canvas, right? Go to canvas, go to the still pictures. Okay, sometimes it works, sometimes it doesn't work. Go to the still pictures, open up the very first picture if it is the test. Otherwise, open up the that day's lecture still picture that's relevant. Click on that, glance at it, and then click to the next picture. Should we just do that for like maybe 5-10 minutes? Yes or no?
Yes, please.
Yes. Okay. Maybe very quickly. I'm not sure if you guys want that, but then let's just let's see. Where is my canvas? Hold on for a second. I have no canvas. No, I have canvas open. Okay. My canvas is here. This is not open. There you go. Canvas. Canvas login. A second. I'll just do it very fast. Modules. Let me share screen. Share screen, and this is molecule, not molecule. This is screen number 2. Why did I say molecule? So yeah, I'm just going to click on this. Sometimes it doesn't work when the. Okay. You guys see the screen, right? Blah blah blah. This is our first lecture. Next. It's actually a really good thing. I strongly recommend that you consider doing this. Different atoms, different molecules. This is the very general rant from your instructor. Okay, we talked about that. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Keep track of these major elements. Keep track of the fact that the extreme right column is all inert gases. They're full. Level 1 is full, level 2 is full, level 3 is full, level 4 is full, level 5 is full. Fluorine, chlorine, bromine, iodide. Okay. Electronic configuration will come pretty soon. We talked about different shells, 1, 2, 3, 4. Lewis dot structure, we talked about that. Boron is important for today. Okay. This is how you do the Lewis dot structure. I don't know which element this is. 5. Yeah, we were talking about boron. So that's fair game. Okay. Hi, Julian. Hi, Alicia. And then boron. Okay, let's go back for a second. I don't know why am I so keen on talking about boron today. Boron has 3 electrons in its outermost shell. This is the last shell. So it's 1s2, 2s2, 2p1. 2 of these electrons in the outermost shell are in 2s level, and then 1 in 2p. 3 electrons. So it's still not fully happy. In BH3, it's an unhappy molecule because this site is open. The south quadrant is empty, no electrons. So it's not, it wants to feel like neon, but it cannot feel like neon because it's still missing 2 electrons. So if lithium wants to feel like somebody, lithium has 1s2, 2s1. What would it do to be close to a celebrity? It'll not add 7 electrons to look like neon, but it'll lose its number 2 level electron to look like helium. You guys got that? Let's think about that for a second. What I just said. I said if lithium wants to look like or feel like an inert atom, it will not do something stupid like adding 7 electrons to make it look like a neon, which is probably going to destroy the world, because the universe, because that's going to be involving a lot of energy. If you add 7 electrons to lithium, that means lithium will be lithium 7 minus. That sounds crazy. That sounds like a tremendously high amount of energy. So it'll rather lose the electron, become lithium plus, lithium ion, right? And look like helium. Remember what I just said. I'm preparing you for the test. Hydrogen, helium, lithium, beryllium, boron. Where is our carbon? There is no carbon here in this discussion. We use the motel, metaphor. We use the circles, the spheres, 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. One spin up, one spin down. That's one rule. We talked about that. The rules are important, okay? The rules are important today. Hi, Monique. You can see me right now with sharing screen. So Aufbau principle is important. Pauli exclusion principle is important. This is Pauli exclusion principle. I don't know why am I doing a review right now. I shouldn't be doing that. Something is not right. Hund's rule. This is Hund's rule. 2 electrons when they should be going in with opposite scale, following opposite spin, following Pauli exclusion principle, Hund comes in and says, no, that's not right, because there is a degenerate orbital, same energy. You should untangle them, unpair them, and put this guy, let him have his own rule. So it goes up with an up spin. Okay, that's Hund. That's Hund. That's Pauli, and this is Aufbau. You don't write down to up, you write top down. 1, 2, 3, 4, 5. Let's pause for like 5 seconds. Okay. All right, everybody. I am dropping way too many hints. And you should not be checking book. You should not be looking at screen or texting someone about the answers. You should not be doing that, because if you do that, you're going to be in trouble. You have to do 32 questions in 60 minutes, not 32, 28. So you have like a little more than 2 minutes, but you might feel a little rushed. Okay. Maximum number of electrons in level 1, 2. We talked about it. Maximum number of electrons in level 2, 8, 18, 32. Okay, there is not much to see here. Come on, let's move. Come on, Joe. Let's go to the next room. This room in the museum has nothing. Okay, we are talking about Lewis dot structure of elements. Aluminum has 3 electrons because it's right below here. What's common between 2 elements in the same column? Number of valence electrons. What's common here along the same row? It's the same darn shell. Shell 1. Shell 2 is getting filled up. Shell 3 is getting filled up. Okay. Blah, blah, blah. Okay, we started doing Lewis dot structure for molecules. You know how to do that? Show all the electrons. Boron, ammonia, water, HI, hydriodic acid, hydrochloric acid, hydrofluoric acid, etc., etc. Size decreases left to right, size increases top to bottom. Non-polar, 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 kind of. We talked about the numbers, the ranges. What's the range? I think we have it here somewhere. The standard, yeah, there you go, on the right side. down here. 0 to 0.5 electronegativity difference, nonpolar. 0.5 to 1.9, it's still a covalent bond, but it's polar. Greater than 1.9, it's an ionic bond. Pause for 5 seconds. 1, 5, done. All right. That's how I learned how to count. Okay, we started talking about hybridization. We are getting to the hybridization story because this is not it, but this is expected. That's not how we find methane. That's not how we find methane. We find all 4 bonds same. So, well, excited state carbon goes through hybridization. That must be the next picture. Yep. So hybridization happens. They get mixed up. You get 4 degenerate hybrid orbitals right here. That's the whole thing. Don't think too much about hybridization. That's it. And see, this is a CH4 molecule. This is a CH bond. The shape of the CH bond, the molecule is tetrahedral. We talked about it, I'm sure, in this. There you go. We talked about the shape, the box, the cube, and this is how it is. And you draw this molecule in all kinds of ways. Like you can draw ammonia like this, like a little tripod, like a little spaceship landed on Earth, and that's the head of the alien popping up from the top with, opening. This is linear. This is trigonal pyramid. Water is bent, and CH4 is a perfect tetrahedral. sp3. They're all sp3. All right. I think we talked about alkane, alkene, alkyne. We have done it recently. Yesterday, I think, something like that. We started listing all the entire laundry list, carbon 1 through carbon 10, methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, decane. Then we learned how to do skeletal diagram. Some of you still may have confusion about the skeletal diagram. Every end, every bend is a carbon. That's important. Don't forget that. Alkane, only single bonds. Alkene, at least 1 double bond. Alkyne, at least 1 triple bond. These are all hydrocarbons. Nomenclature, my favorite topic. Single bonds can rotate. Oh, no. We talked about the bond rotation, conformations. Okay, this is how you can draw a molecule in 3D, sp3. What did we talk about here? Sigma bonds. Okay, I explained what sigma bond is. Axial overlap. Okay, all right, we did that. These bonds can rotate. So these two guys are the same. There's no difference. This is better because now you can appreciate it. If you think hard, hi Monique. If you think hard, I waved my hand, but I realized that I'm sharing screen. Carbon 2 and carbon 3, if you look down, this is staggered. If you can imagine that. Imagine your eyes here and you're looking down this bond and you are seeing that circle Newman projection. The front methyl group is down, the back methyl group is up. Everybody is far away from each other. This is the best conformation. This is a staggered conformation. This is the way it's drawn here, like a little stepping stool. This is eclipsed. This is bad. This is the worst conformation. This is the best conformation. I just dropped some hints. Let's pause for 10 seconds. Look at this. I want everyone to get like 90% and above in this midterm without doing any funny business. I hope you guys don't do any funny business. I trust you, and usually when someone trusts, usually people reciprocate. It's kind of funny, like our son had a story from 6th grade. The teacher left the room when she gave them an exam and they could have cheated. And before she left the room, she said, well, I trust you guys and I hope that you guys reciprocate. And they were 6th graders and they are not saints. Many of them are, their values of common core human values were very compromised. But then our son came home and he said that this was amazing. Mrs. Ulner left the room and nobody cheated. They didn't want to let her down. I'm like, wow, that's great. This is important, knowing all your functional groups. I mean, alkyl chains, methyl, ethyl, propyl, butyl, blah, blah, blah. And then you can have the branched ones. Isopropyl, isobutyl, sec-butyl, and tert-butyl. Look at it for a second. Stare at that. Make sure you know that very well. You know the rules. I don't have to go through the rules. It's kind of boring. Okay. What did we do here? Okay, we just learned different nomenclatures. Yeah. Find the longest chain. Don't be fooled. This is important, guys. Find the longest chain. Look at the molecule very carefully. Okay. The longest chain may not be the longest chain that looks like the longest chain. Do not always look for the horizontal part being the longest chain. Like the way this molecule is drawn here. That's not the longest chain. The longest chain is, all the way up to 5, and then you have to take a down path, 6 and 7. It's a heptane. It's not a hexane. That will be wrong. Okay. Just giving you some heads up and some warnings. All right, let's see what's next. And probably more nomenclature. Oh man. Okay, you guys can figure it out. Okay. Alphabetical order is important, and the numbering happens, we talked about it a lot. All right, what else? That looks like some really weird caterpillar in your back here. Intermolecular distance, we talked about something funny, boiling point and melting point and stuff like that. Remember that less branched they are, closer there. If they're closer, it's going to be more difficult for you to separate two people in a very close-knit family. Okay, and this is not a very close-knit family. It's branched and they're kind of far away from each other. They don't want to be too close to each other. Because of the branches, it's very difficult for them to get very close. Okay.
Would it be the same for melting? I'm sorry.
Yeah. Same for melting.
Oh, it'd be the same for melting point too?
Yeah, because it's the same concept.
Okay.
It's you're separating the molecules, you're increasing the intermolecular distance. It just, the distance is smaller when it's solid. Distance is a little bit more when they're liquid. Distance is much more when they're gas. So it's the same concept. The concept, the fundamental guidelines don't change. Okay, Natalie? All right, next. Okay, this is the Newman projection, conformations, eclipse, and staggered. Okay. I shouldn't be doing what I'm doing. Cyclic molecules. The smallest cyclic alkane is cyclopropane because you need 3 points to make a cycle. Not really a cycle, but a closed molecule. Cyclobutane, cyclopentane, cyclohexane. Okay, what else? Yeah, they came from their parent alkanes. Propane becomes cyclopropane, butane, cyclobutane, cyclopentane, and cyclohexane. The coolest among the group is cyclohexane. You know why now? We talked about it. We talked about the fact that it's not just a hexagon. It looks pretty. I mean, if you draw it this way, you would say that the hydrogens are safe. All the 6 hydrogens are almost in similar situation, but actually it's not. In reality, it's sitting in 2 different locations. One type of hydrogen is sitting up here. Another type of hydrogen is sitting down here, axial and equatorial. Axial up, axial down, Axial up, axial down, axial up, axial down. It goes through boat. Boat is bad because you have a flagpole going on and you have 2 carbons here and 2 carbons there. They're eclipsed. In a cyclohexane chair, every 2 adjacent carbons are staggered. So it's good. They're all perfect tetrahedral. Not well, I should not say perfect because there are 2 hydrogens and it's in a ring. So they're almost perfect. And we just kind of ranted on the same thing, footrest, backrest, sitting area. I know that we had a discussion about this chair looking kind of weird, but this chair is the same thing. It's just the angle of vision is different where you're looking at the molecule from. You guys got it. I think it's not that difficult. So chairs flip to the other chair. Headrest becomes backrest. I mean footrest. Sorry, backrest becomes footrest, and footrest becomes backrest. And somebody should think about building a chair like this in your backyard. We talked about substituted cycloalkanes, methyl cyclopropane. I talked about, I think I made me hungry. I made me crave for chocolate. Hershey's Kiss, this is a kite. That's also another kite. This is a kite that needed some weight because the guy who built the kite screwed up. This side was too heavy. We actually had to do that, but I was flying kite when I was a kid. All right, so when you put a group on a cyclohexane, the cyclohexane substituent, the branch, can either occupy down here axial or equatorial. Then we talked about the fact that axial is bad. Why is it bad? 1,3 diaxial interaction. This guy doesn't have any such problem. Remember, I made the model and it kind of looked like a stingray to me, or like a spaceship, or like a submarine. We talked about that. Multiple groups, which one would be the best? Well, ideally both equatorial, but if I have a choice between equatorial and axial, I would put the big group equatorial and the small group axial because that's a better compromise. Between B and C, C is better because you're putting the bigger guy out of everyone's way and the smaller guy, where there is some problem, some bumping, little crowded. Okay, so D is best, C is okay. Sorry, what did I say? Yeah, D is best, C is good, B is fair, and A is bad. Let's pause for 10 seconds. But see, you have no idea what's going on if you just draw it in 2D. 2D does nothing useful. This was definitely not in my plan during the review, but that's okay, I'm not regretting it. Okay, we use the big box and the small box example to kind of like help you understand the concept. Why should I put the big group equatorial and small group axial? Because of this reason. You want to put like a small box up here when there is problem. You want to put the big guy somewhere else if you have a choice. All right. What else? Alkenes. We talked about alkane on the top. No other reason but give you some reference. That's it. That this is how alkene happens. For alkene to happen, you need to play the game a little differently because you got this weird pi bond, and the pi bond is only made from unhybridized, completely pure and natural p orbitals. So you need to save this aside. You can't touch this when you're mixing things up. When you're mixing things up, you mix one s and 2p. So the hybridization is not called sp3, the hybridization is called sp2 because 1s and 2p orbitals are going in the hook part. You get 3 equivalent sp2 orbitals. They take up the shape of like planar 120 degrees apart, like 120, 120, 120, and then they go in, and this entire part of the molecule, the carbons and the 4 hydrogens, are perfectly planar because the pz orbital is sticking out from here, up and down and up and down. They need to be perfectly parallel to make a pi bond. Otherwise, pi bond doesn't happen if there is an angle. So in order for them to be parallel, the p orbitals, this molecule has to be perfectly planar. So the double bond and the vicinity is usually very, very planar. All right, I think we're almost coming to the end. Yeah, I did it in like one color. I don't know why. Sometimes single color is easier to see. We did like a Lewis start structure or something like that here. Ground state, excited state, ground state, excited state, hybridized state. 2p hasn't been touched. The 2p's are making the pi bond. These 2 sp2 orbitals are making the carbon-carbon sigma bond, and the rest are used for hydrogen, for picking hydrogens. Yeah. What else? I think this might be our last, no, not last, almost to the end. So so if I throw an alkene and I start asking you questions, I can ask you, what's the hybridization here? You should say sp2. What's this bond made out of? sp2 and 1s. What's that bond made out of? sp2 and sp2. What's this pi bond made out of? 2p and 2p. What's the angle? Around 120. What's the shape? Planar. Pause for 10 seconds. 1, 5.5, 6.2, 10. Okay, this part of the molecule is planar. What's planar? The elements sitting at the end of the double bond, carbon 1 and carbon 2, and what they're directly attached to, nothing else. This guy, this guy, this guy, this guy, this guy, and this guy. That's it. These 3 are not planar. Remember, this is a tetrahedral guy. So this is probably on the whiteboard. This is up and that's down. And it's up and down. That means it's not planar. It's not on the whiteboard plane or your computer screen plane. Computer screen plane has these 4 things on that plane, sitting on that plane, on the surface. And this bond, carbon 2, carbon 3 bond, can spin. If it is spinning, this is like a propeller. This is like the propellers of a Cessna, like a single engine aircraft. It's spinning. And sometimes H6 is here. Sometimes H6 could be above the plane. Sometimes H6 could be below. So it's spinning around like a little propeller. Okay. So make sure that you don't make a mistake. This is propene. This is ethene. This is butene. You need to start putting the number as the molecule gets longer. This is not just butene. This is 2 butene. And you can have 1 butene. And this is also not just 2 butene, because 2 butene can be E or Z. Oh, we spent an hour doing this. We talked a lot about E and Z. EZ doesn't make sense here. Cis trans doesn't make sense here, because across this double bond, you have this big guy here, the ethyl group. You have a hydrogen here. You need to start imagining like a chemist. There is a hydrogen here, and there is a hydrogen here. I think I was talking to Josie at the end of the class yesterday, and I needed to realize, I realized that I needed to tell you guys that this bond is not linear. This bond is slanted. When it's slanted, like That's a slant, angle, and that's also an angle. Whenever you put these things in angle, these groups are stuck. If I have a, like over here, the methyl groups are stuck for the rest of their life. They have to see each other from close proximity. The hydrogens are stuck here. So cis-butene is cis-butene, pretty much. This is trans-butene. Trans means E. Cis means Z. Z, cis. Same side. Okay, let's pause. Since we're doing a review, why not we do a proper review? I'm not going to rush through it. Okay. I use some, I don't know, some shapes. This is Z, this is E. Opposite side, same side. Same discussion, just different examples. This is 2-hexene. 2-hexene can, you need to specify E or Z. This is E. Why? Start thinking about it. This is the double bond. Focus on the double bond. One slanted group, another slanted group, one angle group. We haven't written that. Hydrogen. There is a hydrogen here. There is a methyl group here. So for the left side of the double bond, that's the large group. And the hydrogen, which is not shown here, that's the tiny group. For the right side, methyl is the large group and hydrogen is the small group. So the large group on the right and the large group on the left, they're not on the same side, they're on the opposite side. So this is E, or trans. How would the Z version of it look like? Something like this. Okay. Cis, trans, cis is Z, trans is Z. I can't help you with any trick to remember why E should be trans. I have no idea. I don't know what we are doing here. Okay, I was talking to Josie about it. We're just kind of going through like, what is cis and what is trans? If you watch the video, you'll see that. Okay, I was just talking about, I think I was talking about skeletal diagrams and making sure you follow what's going on here. CH3, CH2, CH3. Sometimes I have seen Chem 128B students screwing up skeletal diagram even at the end of their series of organic chemistry. 3 hydrogens here, 2 and 3. 3, 2, 2, 3. CH3, CH2, CH2, CH3. This guy, CH3, CH2, CH. This carbon already is using his 3 tentacles to bond with 3 carbons. 1 carbon down here, 1 carbon up here, 1 carbon here. So it's got 1 tentacle left, which is picking up a hydrogen. So there is a CH here. That's a CH3, CH2, CH3. CH3, CH2, CH, CH, CH3, CH3, CH2, CH3, CH2, CH2, CH3, CH, CH2, because it's a double bond. CH3, CH, CH, CH3. 1 hydrogen, another hydrogen. You don't draw a double bond linearly because that's just wrong. It is a very, very wrong thing to do. It's forbidden because the angle is supposed to be roughly 120. Opposite side, 120, E, Z. I kind of spelled it out like all the hydrogens. If you draw trans 2-butene or E2-butene, what's everywhere? I mean, if I show all the carbons and hydrogens, what does it look like? So we drew the blue E2-butene, trans-2-butene, and then started drawing the carbons in red and hydrogens in green. CH3, CH, CH, CH3. Stare at it for like 25 seconds. Oh, that's different. Okay, I'm stopping sharing. Let's go to the front camera. Maybe we'll take like I want you guys to kind of think about what we just discussed. So let's take a 5-minute break. Let you guys ponder. Let's come back. According to my computer, it's 7:53. Let's come back at 8. Okay, let's come back at 8. I'm going to shut down my camera and my microphone. Let's come back sharp at 8.